All right, brace yourselves. Here comes some math. So this is a simplified version of a 1s atomic wave function. So this is the function that describes a 1s electron, and these are nice and simple. In fact, they are merely just an exponential decay. So this is just a bunch of constants. A0 is a length parameter. It's the length of it's half the length of the hydrogen of the bond in H2. And this is just saying that the electron density for a 1s electron, its probability density, just drops off exponentially as you go away from the distance, and this r is the distance from the nucleus. So this is a 1s wave function centered on a single atom, which we're calling hydrogen atom A. And this is a phi because, well, that's what we use for these atomic wave functions. And consider a 1s electron on a neighboring atom, hydrogen atom B. Its wave function would look like this, and this function is centered on the nucleus B. This wave function is centered on nucleus A. Now, when I say that the molecular orbitals or the molecular states are just linear combinations of these, that's the exact algebra definition of linear combination. And in particular, I could say this, that my molecular wave function is equal to this wave function squared plus this wave function squared plus twice the product of them times a constant. And that is the wave function for a molecular orbital or a molecular electron state. And it looks like this. So, okay, pay attention. There's a lot to unpack in this graph. Now, what I want you to look at is the blue line here is just these two functions plotted on the same graph. So the nucleus of hydrogen atom A is at position 0, and the nucleus of atom B is at position, it's about 1.1 or something like that. And the blue line here kind of shows the exponential decay of the electron probability density, from electron in hydrogen atom A, and it's almost the same exact thing, not almost, it is the same exact thing for the electron of hydrogen atom B. Now, remember that this new molecular orbital wave function is more than just the sum of the two. And so I've plotted out this function here, and that's what the red line is. And look at the difference. So these bars here show where the two nuclei are. Notice how the red bar is higher in between the nuclei, and it's actually less on outside. And think back to when we were first talking about bonding to begin with. How do you get nuclei to not fly apart? You put negatively charged particles in between them to block them from repelling each other because they both have positive, both nuclei have positive charges. And the green line here is the difference between the red line and the blue line. So when the green line is above this 0 line here, that means there's more electron density at that position than there is when these electrons are not interacting with the other nucleus. And when it drops down, it means there's less electron density at that position. So look at this function, and what this does is it actually adds a little bit of electron density smack dab in between the nuclei and steals some away from the outside. But that's what you want to keep these two nuclei from flying apart. You want to put the electron density in the middle. So an electron with this wave function would help, by virtue of where its position in space is, would actually help those two atoms, those two nuclei, from sticking together. And it does. And for that reason, this is called a bonding molecular orbital or a bonding electron state. Now there is a rule, much like for the hybridization rules, that if you combine two atomic functions, you get two functions out. In this case, we'll get two molecular functions out. So let's look at what the other one is. So we're starting with the same two atomic wave functions, the exponential decays, centered around atom A and atom B. Except now it is the A wave function squared plus the B wave function squared minus twice the product of AB. So the difference here was, the plus or the minus for this last term right here. And it turns out that makes a very big difference. So I've got a similar graph here. Again, the blue line is if you just put the functions separate, if you basically just added the functions together and put them on the same graph, you get this. And there is some electron density in the middle, just like there was before. Now the red line in this case is this new molecular wave function. And you will note that it actually has less electron density in between the nuclei. Again, these two vertical lines right here. And the density is actually increased on the outside of the molecule. And this green line is the difference between the two. So again, we have lost electron density in between the nuclei, and we have gained electron density in the regions outside of the nuclei, not in between them. And this is exactly what you would not want to for an electron to be like if you wanted to hold a molecule together. These electrons spend less time in between the atoms, spend more time on the outer, outside of the atoms, which means that they do not block the nuclei from each other. They feel the full positive charge. So an electron adopting this position in space would actually cause the molecule to fly apart. Not what we want. So this would we would call an anti-bonding molecular orbital or an anti-bonding state. And one thing I want to add, that there is a spot here, smack dab in the middle, where the value of this new wave function is exactly 0. So there is absolutely no chance of ever finding the electron smack dab in the middle. So this is a node, just like we called just like we had nodes with atomic electron states. There are nodes in these molecular electron states as well. And also that, so what are the relative energies of these two states? Well, it's probably what you would expect.